It is the 2nd of September 2025, approximately 9:36 a.m. Let's get right into it with these exercises from Chapter 1. The role of algorithms in computing. So for the first exercise, we're asked to describe a real-world example that requires sorting. We are also asked to describe one that requires finding the shortest distance between 2 points. So let's think about that for a bit. Well, what's the intuitional approach for this? Well, sorting is like putting exam papers in alphabetical order so the teacher can enter grades quickly, right? Finding the shortest distance is like using Google Maps to walk from the dorm to the library. So let's talk about that more in depth. So, sorting takes a sequence of items with keys and produces a permutation in non-decreasing order. Examples include sort, merge sort, include insertion sort, sorry. Might say that's intentional because I have to literally insert that there. Merge sort or quick sort. It's likely, well, there's others, but it's the ones that I'll mention for now. Now, the shortest distance problem, well, that can be formalized as finding a minimum weight path in a graph, G is equal to vertices, edges, weight. This sort of thing is solvable with Dijkstra's algorithm. For non-negative weights. Or Bellman Ford. If negative edges are possible. It's kind of counterintuitive, the idea of negative edges, but that's sort of explained away in the theory of the thing. So that's looking at that with full vigor of formalization in mind, approaching each section as is its own sort of problem to extrapolate upon. So we have these methods of sorting. We have these methods of finding the shortest distance. Whether or not you can look at that through geodesics is something else to look at on your own. But yeah, let's turn to exercise 2 right after I check this real quick. This is a different room, so I don't know how the sound is in here. But I think, we basically covered that question within the intuitive fashion. The rigor is just something else to add to the mix. So, the second exercise, it asks us, other than speed, what other measures of efficiency might you need to consider in a real-world setting? Right, so intuitively speaking, a program that runs fast but crashes, drains the battery, or uses all the memory is not efficient, right? If it runs fast but has no depth to it, for instance, chatbots before ChatGPT and stuff like that, you get these answers, but they're wildly askew, and they're just completely worthless, right? It's a waste of my time, waste of your time, but waste of everyone's time. So, just intuitively speaking, there are things that count for more than speed whenever we're talking about efficiency. It's a factor, but it's not the only factor. So, additional efficiency measures well, these include, for instance, space complexity, so auxiliary and peak memory usage. You can sort of look at that with RAM if you look at Task Manager, right? So the input-output cost, and cache locality. Energy / power consumption. It uses a lot of power, and all you're getting is just something that's completely tangential. Probably aren't going to pursue that as a long-term strategy. It's a long-term mechanism, it's a long-term tool. Scalability. Right, so it's like, well, the Germans in World War II, they had better, arguably better tanks on average, but if the Soviets can crank out 5, 10, 15, 20 decent tanks, well, quantity is a quality of its own, right? So, leave it at that. Throughput and latency, right? That all goes sort of into that as well. Then there's numerical stability. And precision in scientific computing. You don't want it to fall apart if it hits a number. I mean, there are certain numbers. You can go a certain length, and then it's like, well, everything we have will kind of fall apart if you try to put that into any calculator. But it's more like, okay, what sort of numerical range are we working with? And if we say that it's working within that numerical range, can we guarantee that it's going to compute that number, take that number into account, and work with precision to a certain limit that we state beforehand every single time? It's like, that's what we want. So, reliability, fault tolerance, maintainability. These are all good things, and these are all the sort of things that you have to take into account whenever we're talking about the efficiency of an algorithm, whether we use it as a tool, what have you. So, exercise 3, well, 1.1-3, that asks us to select a data structure that we've seen and to discuss its strengths and limitations. So I guess, well, sort of walk here, check that. Well, intuitively speaking, a hash table, that's like, you know, like cubbies with labels, right? Put something in by label and you can grab it instantly. That's the idea. Now, speaking more rigorously, the strengths of this well, we have big O of 1 expected time. for insert /search /delete. This is ideal for membership tests, right? Scan your card. And frequency counts. What are some of the drawbacks? What are some of the limitations of hash table though? Well, no ordering. So you can't support range queries or next, right? So that's a problem. And you have the worst case big O of n under many collisions. Memory overhead and resizing, that's a difficult thing, right? It's a limitation. Performance. Depends on hash function quality. And if one of those is not a good quality, well, you've got a problem. Balanced BSTs, well, those give big O log n operations with ordering guarantees. So something to consider in place for what you're using. So there we go. That fulfills exercise 3. Well, we'll do one more, and we'll call it quits for now. So exercise 4, 1.1-4, asks how are the shortest path and traveling salesman problems given, well, similar. So it gives both of them in the text, but how are they different? So intuitively speaking, both are about finding the best route. The shortest path is one trip. The traveling salesman problem, though, that's visiting every city exactly once. So how do we say that more rigorously? Well, the shortest path problem finds a minimum weight path between two vertices and is solvable in polynomial time. Right? So, you know, refer back to De Zijkstra and Bellman-Ford. Traveling salesman problem seeks a minimum Hamiltonian cycle and is NP hard. So what can we say about this in general? Well, the shortest path has efficient algorithms. The shortest path problem has efficient algorithms. Whereas the traveling salesman problem requires exponential time exact methods or approximation schemes. So one of these things you're going to be sort of, you know, you kind of have a open and shut case for the shortest path problem, right? Versus the traveling salesman problem, it's like, well, how many iterations worth of approximating do you want? So that's all we can afford for now, time-wise. That's it.